Yeah, my name's Jody Dado. I'm one of the business development managers here at Iris Incorporated. Here at Iris, we manufacture infrared inspection windows. We have our Safe Connect product lines as well as other EMSDs. We're also reintroducing or engineering our Delta T product that will get us into the IoT market sector for online monitoring purposes. But today's presentation, we're going to focus on improving your maintenance program through operator-driven reliability. So we want to start off by asking yourself the following questions. What is your dependence on the electrical energy and control systems? What are the consequences of an unplanned mishap in your electrical systems? How long will it take you to recover from an unplanned outage, and how are you going to improve your electrical distribution system's reliability? If you don't change the way you think, you're never going to move forward. This is one of Martin's favorite slides. The same old thinking results in the same old results. We've always been kind of into the mind frame of doing more of a time-based maintenance program on a lot of equipment. And today we want to go and introduce you into operator-driven reliability maintenance program. So we'll start off here. This is a study that was done by Winston Leday, and he wrote an enormous amount of books on reliability and is considered an expert in the field of reliability. And what we're doing is trying to introduce people to the concept of failure, how things fell, how things fell. It's very important to the foundation of how Iris and how we saw our products. But basically, here in the study, they took 30 identical components. They ran them all in identical conditions, load, speed, etc. And they logged when they failed. And what they found is things do not fail in the same way. They found that the things failed randomly. And if you redraw the histogram with the same data, you'll see that the risk of failure is constant. Obviously, things fell all the time. However, the way things fell and the timelines where they fell are random. So I guess you can say things fell constantly, but they fell randomly. A lot of our clients talk about MTBF, the mean time between failure, and you designed to choose a time period to do maintenance before things fell. So taking into consideration the redrawn histogram here, how things fell, if you're doing a maintenance every 5 days, you're going to be overtaining 50% of the fleet. Every 10 days, you're going to have the possibility of overlooking things that are going to fail. So it's important, very important to recognize that things fell constantly. However, they fell randomly. And trying to use a time-based maintenance schedule is totally impractical on your random failure approach. So your maintenance has to be random. Basically, time-based failure mechanism doesn't work. And this is a study that was done by John Schultz and Ron Moore. And so don't assume your planned maintenance is correct. You could be wrong. Consider one analysis of 20,000 planned maintenance tasks. The routines they studied, were they adequate for the task? And well, here's what they found. 11% of the planned maintenance tasks were you could use as is. 8%, which is 1,600 tasks, could be deleted altogether as they had no relevance. 33% should be replaced with a CBM, a condition-based maintenance program. And that's 6,600 tasks that could be transferred to CBM. 26% had to be re-engineered because the PMs were not adequate. 7% were transferred to operations, ODR type of scenario that we'll talk about here in a little bit, the operator-driven maintenance program. And 15% were transferred to a lubrication program. So just because you have a planned maintenance guide doesn't mean it's correct, and it probably isn't. And don't assume your vendor PMs are correct as well. And again, this is another study that was done by Ron Moore and Steve Turner. They basically looked at 964 tasks that they got from OEM vendors. And here's what they found. So basically 366 could be used as is. 202 were deleted. They didn't provide any desired results. 222 were extended tasks, or they were done far too often. 116 were new tasks, and 58 were not adequate. They shouldn't have been done, they should have been done more often than what the tasks recommended. So the OEMs, the vendors, they don't consider the running, the operation, startups, the temperatures, the equipment location, etc. A blanket preventative maintenance program or planned approach does not work. And OEMs need to worry about risk, which can result in over maintaining. A study also found that 96 new another 96 new failure modes. So even though the OEMs know you can rely, they know even themselves, they know that you can't just rely on their planned maintenance programs or schedules that they give you with their equipment. So now we'll talk a little bit about the effects of time-based maintenance on infant mortality. Time-based maintenance, scheduling and doing maintenance on a set period of time. So basically, the greatest risk of failure is in the infant mortality stage when you're just starting equipment up. But then if you're doing a time-based maintenance schedule, you'll see that this could be every year, every 6 months, every 1 month that you're taking the equipment down to do a scheduled maintenance on it. So if we're monitoring the condition through IR windows, for example, noting the changes, why am I doing unnecessary maintenance? What does this inject? And what this does is inject defects into the system. The only time you really want to do maintenance is at this point, if you're doing a condition-based maintenance program, you can see that the faults are starting to occur, and that's when you want to take a look and start doing the maintenance. We're all human and we all make mistakes when we're doing unnecessary maintenance. So the point is, you can get rid of all these other scheduled maintenances, because why inject defects into the system if it's running, if it's up and fine. So basically what we're saying is, every time we complete unnecessary time-based maintenance, we reset the infant mortality clock. And you're injecting, let me go back one, and you're injecting basically defects into the system every time we shut the system down. And that's how things fell. So now we'll talk a little bit about the planned time-directed maintenance. If it wasn't broke, but we fixed it anyways, think of your assets like at home, your home appliances or your HVAC system. If everything's running fine, it's not necessary to turn it off and have a technician come in and tear it apart and charge you, whatever it costs these days to do that type of a maintenance, just to let you know that everything's running fine. So if it wasn't fixed, or it wasn't broken, but we fixed it anyways. The greatest risk of defects and failures is at startup. So how can we minimize that risk? The way we minimize that is to do less startups and don't shut down equipment that's running fine. So Rahman Hall says you're 7 to 17 times more likely to introduce defects during startup. BP says incidents are 10 times more likely during startup. The chemical industry reported process safety incidents are 5 times more likely during startup. New equipment can have twice the number of infant mortality defects as existing equipment. And 92% of rotating machinery report to have defects at startup that result in premature failure. By doing unnecessary shutdowns, you're injecting defects into the system constantly, increasing risk of failure exponentially. So now we'll talk a little bit about the reliability process, and this is a chart by Andrew Fraser. So basically, this is the science of reliability, and reliability is purely about defect elimination. The way we design it, buy it, store it, install it, operate it, and maintain it can all cause defects. And that's why this is a point that we're trying to get to is operator-driven reliability. If we're going out to get a new piece of equipment, let's get the operators involved to come in and help us. They can help us out in the design process because they should know the equipment better than anybody. But if it's designed wrong, you're going to inject defects. If it's bought wrong, you're going to inject defects. If it's stored wrong, you're going to inject defects. If at startup, you can inject defects. And of course, if it's defect to begin with, you're going to operate it with defects. And then you're maintaining defects already injected into the system. So the name of the game is to remove the defects. When we remove the defects, we increase the reliability exponentially. Reliability is purely about defect elimination across the board. We cannot maintain our way to reliability. And the name of the game is to remove the defects. So reliability processes is think about all the silos in the process. And again, to get your operators involved with this process. So talking about condition-directed repair, the condition of the equipment will dictate what we do with it. If the equipment is running fine, adequate, and the output is good, do nothing with it. Just inspect it more routinely, but don't shut it down. If it ain't broke, don't fix it. And here's a little fun fact about the Mars rover. The Mars Lunar rover was designed by NASA engineers to last 90 days. How long did it actually last? 14 years. And the reason why it lasted 14 years, because there was no mechanics on Mars to mess with it. The reason it quit working because the batteries couldn't charge any longer. It was at the end of their life cycle. So again, if it ain't broke, don't fix it. So now we'll get into and talk about a little planned maintenance optimization program. If we can optimize the way we maintain and run our equipment, we save a lot of money on maintenance, and that improves the output of the equipment. So ideally, we only want to do planned maintenance when it helps to detect the onset of failure, a condition, examples of condition-based maintenance inspections. We want to avoid the onset of failure, oil changes, filter changes, things of that nature. So, if you have a program where you need to change oil based on the number of hours a piece of equipment's run or something like that, and also based on its condition. Or when we have a known consistent time-based failure mode. An example of that would be like a typical age of wear-related fatigue mode, like bearings in a slurry pump or motor brushes. So, if your motor brushes are falling to 18,000 hours, change them to 17,000 hours. Do it time-based, and there's no redundancy and no more planned maintenance. And then there's a non-detectable, the hidden failures, or a very short potential failure interval, and a high consistency of failure. Use a conservative time-based maintenance to replace the planned maintenance. So an example here would be like, EMOs, emergency stop buttons or breakers. The only time you test them is when the equipment's down. And a time-based planned maintenance dictated by statutory requirements or law. So if it's mandatory, that time maintenance needs to be done, then you got to do it. So the PM planned maintenance optimization, here's some tips. If the failure mode requiring the preventive maintenance or the planned maintenance has little consequences, then stop doing the maintenance. The frequency of the PM considers the rate of the failure and the risk consequence of failure. So higher consequence rate of deterioration equals greater than the higher the frequency of the time you're doing the maintenance. The PMs must be specific. Check motor is not a PM, it's a hope. PMs must include objective criteria that determine if a defect is present or absent. So this brings us to the reliability-centered maintenance logic tree. This is a simple three-stage RMC tree, 3 levels of asset management. And this will help us out a little bit when we start talking more about the operator-driven reliability. But basically, we start with this, in the first box, will failure have an adverse effect on safety, health, or environment? If yes, is there an effective condition monitoring technology or approach? If yes, develop, schedule, and perform condition monitoring tasks. If no, will failure have a direct or adverse effect on production quality or quantity? If yes, then go back to the loop. If no, Will failure result in another economic loss, higher cost, damage to facility or systems? If yes, again, go back to the loop. If no, then you're either going to run to fail or fix on failure. Again, going back to the loop, is there an effective condition monitoring technique or approach? If no, is there an effective preventative maintenance task? If yes, then develop the task schedule and perform planned tasks. If no, redesign the system to accept the failure or the risk. So again, all this is getting us again to why we're kind of pushing the operator-driven reliability program. And one big thing, I think that the term we're using now is the silver tsunami, about all the skilled labor that we're losing in the workforce. Today, we know it's hard to get staff, not to mention skilled staff. And this is an old table here. This is 10 years old, but basically it's true. There's a lot of electronic repairs, electrical engineers, technicians that are leaving the workforce every day. There's an estimate that 10,000 people retire daily. And a lot of those folks are the skilled labor. And, it's just hard to replace those folks. And again, that kind of brings us to get into the operator-driven reliability that we'll get into here. So the ODR is an asset management program that involves operators in the maintenance of assets through the execution of inspection routes, aiming at monitoring some process parameters that may be used to evaluate a component's degradation. ODR encourages interaction with maintenance and other departments as a team to reduce the number of failures, thus improving site-wide asset reliability. The concept of operator-driven reliability, sometimes called operator-based reliability, is an integral part of the overall proactive maintenance strategy where the operator becomes part of the asset care. The ODR concept is like another maintenance strategy known as total productive maintenance, TPM, which was developed in Japan in the early 1960s. ODR uses operators to observe the running condition of their equipment and to make minor corrections if components to do so, if they're competent to do so. By proactively identifying problems, operators can eliminate or reduce failures, thereby increasing reliability. They perform such tasks as cleaning, minor adjustments, lubrication, and simple preventative and corrective tasks traditionally handled by a skilled maintenance technician. These tasks represent a departure from the operator's traditional role as just an equipment operator. So the ODR, operator-driven reliability program, encourages production to interact with maintenance and other departments as a team to reduce the number of failures, thus improving plant-wide asset reliability. So if we think about getting the operator involved, now we can go back to the reliability-centered maintenance tree here, and going back to where we left off. So if there's an effective condition monitoring approach, if that's a yes, can this be managed by an ODR program? If yes, then move to an ODR program. And is there an effective maintenance, preventive maintenance task? If yes, can this be managed by ODR program? And if that's a yes, then move it to an ODR program. If there's no, then develop, schedule, and perform a condition monitoring task. Develop a scheduled and perform more planned maintenance tasks if you cannot get your operator involved. Now I'll talk a little bit about the operator skill matrix. Develop an ODR model to develop the skill levels associated with the abilities and training. Develop visual alarm systems. Re-engineer systems and controls to allow safe, repeatable ODR inspections. Develop an ODR continuous improvement model. Develop process rounds, which require operators to check gauges, visual indicators, and meters to optimize the process parameters. Develop rudimentary data collection platforms using baseline CBM instruments like infrared windows, partial discharge, ultrasound, vibration analysis. Develop operators who not only run their equipment, but they own it. And operators must take the responsibility of keeping the process equipment running in their areas. Regardless of the method used, your operator-driven reliability communications plan must include departmental roles and responsibilities, timing and inspection routes and follow-up paperwork, which can be automated using software and user apps, and feedback systems, expectations, training, and how recognition will be handled in the area. So all this gets to the replacement strategies. Our clients have 1,000 things to do, and we don't need to, give them something else to do. We're just giving them a replacement strategy. Moving towards a design ODR condition-driven model, repair model is a replacement strategy designed to reduce outdated and unnecessary legacy maintenance practices with ODR condition-based inspections while managing the risk of failure. So best practices. What is the best practice? Best practices are working standards, and this is straight from Googling this, Wikipedia. Best practices are working standards or ethical guidelines that provide the best courses of action for each situation. Companies, regulators, or governing bodies can all set best practices for business. Best practices serve as a roadmap for a company on how to do business and provide the best way to deal with problems and issues that arise. Sounds great, but when does a best practice become a better practice? Call it building a better mousetrap. By replacing best with better, we leave room for future changes and flexibility. With better practices, solutions are adaptable from company to company, and we all win. Steps to setting better practices include continually researching our industry and our competitors, openly communicate with all employees, set obtainable metrics, continually evaluate and redefine your current best practices, and manage the change. So we always want to design for safety and reliability. And the error is human. Everybody makes mistakes. So that's why we need to design systems to make them error-proof and make them safer. So this brings up a DFSR. DFSR is a Japanese term, or the pokiyoki is a Japanese term for mistake proofing. Error should not be considered inevitable. Any type of error can be reduced considerably, if not eliminated altogether, using DFSR strategies. DFSR creates safer work environment. It ensures consistency of quality results, makes problems more visible, and lowers the cost of design and cost to manufacture. So pokiyoki, mistake proofing. This slide just shows some of the products that we manufacture here, and that can be used to help mistake proof and make condition-based maintenance and operator-driven maintenance more easy to obtain. So this slide is the impact of designing for liability and safety on the total cost of ownership. So basically, the red line is improvement opportunities. The longer you leave it, the less chance you have for improved opportunities in the acquisition phase. The orange line is the total cost of ownership of an asset without asset management. The yellow line is the total cost of ownership with asset management using, our type of products, other competitors' products. But what the whole point of this slide is showing that you can have almost a 40% total cost of ownership. So if you're operating, if there's an operating like a huge power plant or something like that, that could be an amazing amount of savings there. But as you can see on the green line, as your asset management increases, so does your productivity, your throughput, and availability of the equipment. Now here's something that's on everyone's mind: the reduced carbon footprint. Increased equipment reliability through reduced time-based maintenance has significant impacts on our carbon footprint and is driving the implementation of efficient, reliability-based equipment management programs. Here's some of the benefits. The reduction in downtime. So again, getting back, this is some of the benefits of using like an ODR and and getting away from a time-based maintenance program and getting more into a condition-based maintenance program. So you do have reduced downtime, reduction in spare parts, reduction in lubricants and service items, the reduction of waste, the increased availability of skilled manpower, the reduction in shipping and support costs, the increased manufacturing through increased asset utilization, and increased asset availability, less shutdowns. So everyone is looking how to reduce their carbon footprint, and this is an easy win. Not doing unnecessary shutdowns, not shipping parts, storing parts, not throwing old parts away. Reducing oil is a huge, benefit for all of us for the carbon footprint. Now I'll talk about the effects of the operator-driven reliability maintenance plan on asset reliability programs. The increased safety through hazard removal, increased ability to anticipate and plan for repair and interventional tasks, increased time in service, decreased need for intrusive maintenance tasks, inspections, replacements, etc., reduced cost of maintenance in terms of manpower and expenditures for replacement parts, and a reduced collateral damage potential through degradation mediation, which is basically you're not tearing equipment apart, that goes to reducing the total cost of ownership. So this is a quote from Edwards Deming, and this is one of Martin Robinson's favorite quotes, the owner of our company here at Iris. Without data, you're just another person with an opinion. So remember, you got to keep an open mind. Nokia rejected Android. Yahoo rejected Google. Kodak turned down digital cameras. Blockbuster rejected Netflix. Need to be prepared to take calculated risks, accept change as it's going to happen. If you refuse to change over time, your methods will become obsolete and time will change you. The information is there. The data is there to support and a move to operator-driven reliability program. And one final thought, design your system and processes to make it easier to do the right thing and harder to do the wrong thing. Thank you for your time and have a good rest of the day.
Okay, Jody, thank you very much for the presentation. Okay, we have a number of questions. Let's is condition monitoring more important in the initial stage?
Yeah, we feel that it's important through the whole stage of, the cost of ownership of equipment. So you're monitoring the condition of the equipment from startup, all the way through, a planned maintenance shutdown.
Okay. Does infant mortality depend on design or installation or independent of both?
Well, I won't go back to the other chart, but the one chart, infant mortality is can be a fault of everything that we talked about. The cost of if it's designed wrong, if it's purchased wrong, if it's set up wrong, if it's maintained wrong, all those will have an effect on infant mortality. But basically, infant mortality drives the fact that every time you shut something down, then turn it back on, that increases the risk of injecting defects into the system. And as that one graph showed, the more that you inject defects, the more apt are you to have failure in the equipment.
Okay, great. Is CBM in the warranty period useful for OEMs?
I would say so. Yeah, I don't think it would hurt, because if the OEM warranties something, say for a year, and usually that's all you get from an OEM is a year warranty. But if you're if you're monitoring its condition and doing operator-driven type maintenance, then I don't see how it would hurt at all to have condition-based monitoring, an online monitoring system. even if it's still under warranty, because you know, if something fails, then it's going to bring your process down at the end of the day.
Okay. Here's a comment from Jeffrey. A great point on the process rounds. And you hit the nail on the head on collection of the data on platforms so staff can review the data and overlap it with alarm and comms data as part of root cause assessment. Any reaction to that?
No, I agree with that 100%.
Okay. Was the failure rate seen to be higher after the lockdowns and shutdowns? Oh, good question.
Actually, that's a good question. And we
Yeah.
were talking about that yesterday. Actually, the failure rates decreased because there were less preventative maintenances and planned maintenances being done to the equipment. So what we saw during COVID is that actual equipment defects were decreased exponentially, actually, as compared to, you know, full-blown maintenance program turning off equipment that didn't need to be turned off.
Yeah, and I want to add to your earlier comment that the average age of an industrial electrician in North America now is 59 years old.
I know, that's incredible. And we were looking at data yesterday that almost 10,000 people retire a day, which is crazy. I didn't know that number was that high. It sounds awful high, but and then but you're correct. I mean, 59, you know, folks are typically just a couple of years away from retirement at that point.
Right.
And so that's why.
So what is the impact? What is the impact of that kind of loss rate to the industry on maintenance programs?
Yeah. And again, that's why I don't know what the full impact would be. I can't really talk to that. I just know that if you have less skilled trade and say, you know, in your plant or factory, you know, if you don't have, you know, the electricians to go around and do their jobs, or as many of them, then that's why we want to say, and that's why our point is here is get the operators involved, you know, give them more ownership into their equipment that they're running, and let them take the ownership of it. And we see that in a lot of the factories and a lot of the plants that we tour now and that we go to help our customers out. And that's going to ease you know, as these skilled laborers, these guys are retiring, that's definitely going to help ease the pain of a maintenance program if you can get your operators involved to do the minimal tasks. Like, you know, the example I use, you know, my wife at home, she can obviously look at a filter in the HVAC system and say, hey, this thing's dirty, it needs replaced. You know, so if she can do that at home, you know, we can get these operators to help out, you know, on the equipment that they're running, and give them more responsibility and ownership other than just being operators of their equipment.
What is the impact of maintenance programs, software programs in the maintenance environment?
That I don't know. I know we're developing a software program called Delta T that will help you monitor, you know, online temperature changes. But that's, you know, something that we're in the works with here now. But I know there's several other companies that do have asset monitoring programs out there, and it seems to have, you know, a great impact because you're getting less and less. You know, it cuts down on the maintenance routes of the skilled labor.
Right. Well, you're right. Okay. That was a good presentation. Thank you very much.